This is Chapter 3, Composition of Substances and Solutions. Today we are going to talk about finding the molecular or formula mass and also the mole concept. We can find the molecular mass of a molecule by adding up the mass of each atom in the molecule. So let's take water as an example. We have 2 hydrogen atoms and 1 oxygen atom. Add the mass of 2 hydrogens to the mass of 1 oxygen atom to get a total mass of 18.015 for 1 water molecule. The unit is AMU, or atomic mass units. For a covalent or molecular compound, the mass is called the molecular mass or molecular weight. Find the molecular mass of this compound, CHCl3. The answer is 119.37 AMU. Calculate the molecular mass of 1 aspirin molecule, C9H8O4. The answer is 180.15 AMU, and it's calculated by taking 9 times the weight of carbon and adding that to 8 times the weight of hydrogen, and then adding that to 4 times the weight of oxygen. Now find the molecular mass for 1 molecule of ibuprofen, C13H18O2. The answer is 206.27. The mass of an ionic compound is found the same way. Technically, ionic compounds aren't called molecules, so we call the mass a formula mass or formula weight. Find the formula mass of sodium chloride, NaCl. The answer is 58.44 AMU. Ionic compounds rarely exist as just one single unit or compound. They exist in a lattice structure in a positive-negative alternating pattern. When we find the mass of an ionic compound, we only find the mass of the simplest whole number ratio of the compound. Calculate the mass of aluminum sulfate. This one may have been a little bit tricky because of the parentheses and the subscripts. So let's break this down. In aluminum sulfate, we have 2 aluminum atoms. This 3 applies to everything inside the parentheses. We have sulfate, which is SO4 with a 2- charge, and we have 3 of them. So that means we're going to add up the mass of 2 aluminums, and then 3 sulfurs, and then 12 oxygens. And this gives us an answer of 342.14. Now try finding the molecular or formula mass of calcium phosphate. The answer is 310.18 AMU, and this is because we have 3 calciums, we have 2 phosphoruses because of the subscript on the outside of the parentheses, and we have a total of 8 oxygens because of the subscript on the outside of the parentheses. So now you could complete the first problem on problem set 3.1. There are 10 parts, and then you just need to find the formula or molecular weight of each of the 10 compounds. But let's continue and learn some more content so that we can continue and learn more problems from problem 3.1. The unit AMU doesn't really help us. We don't have scales that measure in units of AMU, and even if we did, we can't isolate individual atoms and molecules to weigh them on a scale. And even if we did, the chemical reactions don't happen with just 1 or 2 molecules, but rather with trillions and quadrillions at a time. This is why we need to learn about something called the mole. This is a very important part of chemistry that we will be using throughout the rest of this year. The mole in chemistry has nothing to do with the little animal mole, but in many textbooks and curriculums, this cute little animal has become a mascot of chemistry, if you will. The mole is one specific number or value. In the same way that 1 dozen is equal to 12, 1 pair is equal to 2, a gross is equal to 144, a ream of paper equals 500, 1 mole is equal to 6.02 times 10 to the 23. It is also called Avogadro's number, as Avogadro was one of the scientists who came up with this number. His full name is actually Lorenzo Romano Amadeo Carlo Avogadro. He's usually just called Avogadro for short. We can use this Avogadro's number as a unit conversion. So let's do this practice problem together. How many molecules are in 3.2 moles of H2O? We need to start with what we're given, 3.2 moles of H2O. Then we're going to use a unit conversion, and we're going to use this unit conversion so that we can cancel moles on bottom. Notice you can abbreviate mole as MOL. And then we're going to have 6.02 times 10 to the 23 molecules of H2O on top. In these unit conversions, the unit for Avogadro's number is usually atoms or molecules or some kind of particle, depending on the context. So when we multiply this unit conversion, multiply across the top and divide across the bottom, we end up with an answer of 1.93, rounding to 3 significant figures, times 10 to the 24. And this unit is molecules of H2O. Now you try the next problem on your own and see if you can get the answer. Let's start with what we are first given, 1.08 times 10 to the 24 atoms of hydrogen. Now we're going to use this unit conversion so that we can cancel our unit of atoms of hydrogen. We're going to put 6.02 times 10 to the 23 hydrogen atoms on bottom and the 1 mole on top. That is, in fact, the unit we are looking for. So now if you divide, you should get 1.79. And the unit is moles of hydrogen. But again, how does this help us? We can't count to 6.02 times 10 to the 23rd molecules or atoms. We can't count that if we spent our entire lifetime counting that. Even if you counted to 1,000,000 every second and you did that for 100 years, you would still be still have about 99% of the way to go to get to 6.02 times 10 to the 23rd. So this number is such a ginormous number, it's very hard for us to realize or understand how huge this number is. So we need to relate this huge number to mass, and this will make this concept much easier. And that's what we will do next.